it can either drive the reaction backwards to make a product, or to return back to substrate form, or to make a product. And during this combination, it's called the enzyme substrate complex. This is the basics. We all know this. Now, obviously, different enzymes have different properties, all right? And one of these properties is the velocity or the rate of the reaction. And as it says here, the velocity or the rate of the reaction is determined by measuring how much substrate appears as a function of time, or how much P appears as a function of time. In other words, how fast or slow is the substance being used up, or product is being made by the activity of the enzyme. So the first thing we can calculate is something called initial velocity. This is basically when the enzyme is at its maximum capability of binding and action. But before we see the idea how we calculate that, let's just take a step back. Now, as you know that enzyme kinetics, you need to measure a product over time. So what happens is there's two ways of doing this. There's in a discontinuous or in a continuous fashion. One discontinuous method involves mixing the substrate and enzyme together and measuring the product after a set period of time. Basically, you put the two together and then you leave it entirely, and then you check on it and see how much substrate is left, and then you can calculate accordingly. But the issue is you don't get to see, you don't get this curve here, which is seen in what continuous. Continuous is basically combining both components together, but you just take at different segments of time, different samples, and then you can from there determine. You can start plotting this graph by just seeing how much product is made at each step. Okay. Now, in enzyme kinetics, of course, we use a system called chromogen. That is a brightly colored product. Chromogen, from the term of color, and basically just produces a color once it reaches the end of the product, end of the reaction, signify that khalas, we are done. So then, now next, if you see this graph, as you can see, it's curved. This is how do you get this? From continuous sampling. Now, the first thing we can get is what, as I said, the initial velocity, right? Which is basically how fast it will go. And then there's the Vmax, the maximum velocity, which is basically once you've given as all the substrate it can, this is how strong or how much can the enzyme convert everything in a given period of time. It's the very starting point, or not very starting, sorry. It is more of once you've given everything, it's at maximum occupants. And the enzyme, all the enzymes that you've put, it is being completely occupied and there's maximum binding. But this is how fast, and it will never go above the Vmax. This is its maximum potential. And now the Km. Km is directly an indicator of affinity of the substrate for enzyme at 50% enzyme occupied. Now this formula is important because the way the exam comes, they will expect you to understand that Km is the concentration of the substrate at half Vmax. Keep in mind half Vmax, because especially they would not give you any calculation, nothing, just a number, and they will give you now, as in the question, separate. I will show you an example once we finish. But keep in mind that as well, that Km is an inverse. So if the Km value is higher, the affinity is lower. What does it mean? Because as it says here, it's substrate concentration. Therefore, so let's assume half Vmax, let's assume this is 5, all right? And then the concentration, you have 5. This means that for the enzyme to be able to grab, it needs at a value of 5. And if it's lower, it needs fewer arms. It can catch the substrate more easily. Hence, its Km will be lower, but its affinity is higher. Otherwise, think of affinity as the amount of arms, right? So if we want something to have a higher affinity, more arms. And when we calculate it, that means the Km value is lower. It'll make more sense as we go through further. Well, this is basically the entire concept. The Km is higher, affinity is lower. Lower affinity, higher Km, and vice versa. Now, the linear Michaelis and Menten derived an equation to describe the initial reaction velocity as a function of substrate concentration. Basically, they are able to derive this graph, make a formula using the values mentioned, the Vmax and the Km and the substrate concentration. As you said earlier, it is the measure of the affinity of the substrate. It's an inverse measurement of its substrate affinity. In other words, as I said earlier, More Km, lower affinity. Now, what was the point of this formula? To make this formula, which is a double reciprocal. And what's the point of doing this double reciprocal? Basically, once you plot it, you get straight line. So we went from a curve to a straight line. No, let's pay attention here for a sec. Where's the point? Okay. The few important things we need to understand is this. What is the y-intercept and the x-intercept? If you remember what do these represent and how does the movement goes, any question is now easy. Bear in mind now, and when you plot it, we said it's double reciprocal, right? So the Vmax has now become 1 over Vmax. So whenever now there's a change in the Vmax, there's a change in what axis? The y-axis. And any change in the Km, which is what the affinity, it will occur in the x-axis. Okay. And the slope, it's the gradient. But when it comes to approaching questions, I ideally always look at these two values, and that's all we need to look at. Who's drawing? Anyways, oops. 1 second. My bad, guys. Okay, there we go. Anyways, now why Km and Vmax are important enzyme characteristics? Obviously, because Km varies for enzymes vary widely, and the Km is approximately such a concentration of the enzyme in vivo. Now, if we look here at hexokinase, we know what it does. And if you see at different substrates, it will have different affinities. This basically shows that for the same enzyme, to different substrates, it will act differently. So it has high. Okay, if we look here, 0.4, and compare it to 1.5, which Km is higher? Fructose. Now, what does this mean? What has a higher affinity, to ATP or to fructose? Anyone? Okay. The affinity
Glucose.
Besides glucose, between ATP and fructose, which
ATP.
one? Exactly, because the Km is lower. That's it. Same thing applies, and these are different example of enzymes and so on. And now isoenzymes. What are isoenzymes? They are basically the same kind of enzyme, but they have different kinetics and distributed differently, but they do the same reaction. So if we look at glucokinase and hexokinase, both do the same thing, phosphorylate a glucose. Now, the glucokinase is what? In the liver, and the hexokinase is found in other tissues such as muscle. Now, what does this, now, if you look at this graph here, what can we understand? Now, look here, look at the Km values, look at the Vmax. What has a higher Vmax? Glucokinase. And what has a lower? Hexo. Now, this means obviously in retrospect, what would have a higher Km? It would be glucokinase, and hexokinase have lower. But this means what can respond to a change in glucose to the blood more rapidly? Hexokinase. Excuse me 1 second. Hexokinase. And why is this important? We know that the liver is plays an important role in the glucose metabolism. So it is important to be able to respond faster than other tissues to any change. So this is why, even though in the liver, it will not be, the hexokinase in the liver will not be able to reach the Vmax of in other tissues, but it's able to respond first, unlike the glucokinase, where it would have a lower affinity. So you would need more blood sugar or more glucose in the blood to start seeing more product being made. Is everything good so far?
Can you repeat again?
Okay. If you look at glucokinase and hexokinase, right? And glucokinase, although it has a higher Vmax, so that means it can, and you could think it has more activity, right? In reality, it cannot respond first to any change in the blood sugar. You will notice here that hexokinase, to a very small amount of glucose concentration, it will start acting directly. This is what it basically means. Due to different KMs, these are both the same enzyme, the same function, but they have due to different kinetics. In this case, its affinity is much higher in hexokinase than glucokinase. And this obviously makes sense since we know that the liver plays an important role in glucose homeostasis, right? So it's important for the hexokinase to respond first. Which as it happens here, you can notice that barely, slightly anything more above 0, it directly starts producing it. Although, as I said, that it will not be able to reach the Vmax and start using as much substrate as the other tissues can, it can respond first. And then it says here the liver primarily uses fatty acid oxidation for energy. Most of the cells use fatty acids, glucose, and amino acid energy sources. Most cells use glucose for ATP synthesis. This is all basic information. You'll cover it in other lectures. Now here's a clinical insight to why it's good to know how affinity works. Some people respond to alcohol consumption with facial flushing and rapid heartbeat, symptoms caused by excessive amounts of acetaldehyde in the blood. There are two different isotypes, right? We have one that has a low Km and a high Km. This is basically talking about the Asian glow, because typically people of Asian descent have less tolerance to alcohol, so they get to show the symptoms of acetaldehyde better. How? Because anything with a low Km means there's more affinity. They are able to break down alcohol faster. They get drunk faster, they get hungover harder and faster as well. Because the acetaldehyde dehydrogenase is what's acting, and these products is what causes effects of what do you call it? Hangover. Does that make sense?
Yes, thank you.
Okay. So here, regulation of metabolic pathways. There's different ways a reaction can be induced or inhibited. So in the first example, you can see that A goes to B, goes to C, goes to D, goes to E. And once you reach the product you wanted, خلاص, you don't need to make more. So it will inhibit. So A will no longer be processed. If you look at B, this reaction is obviously talking about, it's a simplified form of, what do you call it? That occurs in the mitochondria, respiration, right? Where you're producing energy. So when you have low energy, so you have low ADP, you have high ADP, obviously it means your body needs energy. So it will push the reaction forward for more respiration. But let's assume you have too much energy, خلاص, you are set. You don't need to exhaust your natural resources into making more energy. So therefore, ATP would inhibit this reaction. And other things which can also, like look at C, it can self-induce. So if there's a high amount of A, you want to process it to get rid of it, so it will push the reaction forward. Tamam? Now, allosteric enzymes are catalysts and sensors. Remember how earlier we talked about the Michaelis-Menten continuous curve, which is the blue line, right? Allosteric enzymes show a sigmoid S shape. Keep this in mind because this can very easily help you distinguish the type of enzyme and the reaction. And especially in question when you see it, you understand what I mean. Now, so what gives it this S shape? It is because we know that allosteric enzymes mean that they undergo a change of shape once in relative to the concentration. Tamam? So what happens is at low concentration, there will be low affinity. Tamam? So as it goes here initially, the reaction is slow, right? There's not, the Vmax isn't. But at a certain point, we reach usually around here, I believe. At a certain point, have Vmax, right? There's enough substrate that will cause a change in shape to make the enzyme more active. Hence, now the sudden increase in its Vmax, giving it this typical S shape, where it was first slow, then fast, right? And that's what gives it its S shape. Hence, it's called a sigmoidal relationship. So the major regulatory step is the rate limiting step. The metabolism are catalyzed by what? Allosteric, which makes sense because only when the certain substrate is enough for the determined rate limiting step, then the reaction can proceed to give the desired product. And here, this term cooperative binding. This is what basically means when the substrate and the enzyme are supporting each other, where if there's more of something, it will push it forward. Now, allosteric enzymes are regulated by several activators and inhibitors. Each allosteric effector binds its own site on each subunit separated from the active site. Basically, this talks about how when there's an effector or an inhibitor, it would not take the place of the enzyme substrate of the enzyme active site. So we wouldn't find the straightforward, obviously. Now, if you see here, look at the positive and look at the negative. What is the change? In the positive, it increased the Vmax, right? It made it change sooner. While, in other words, you would need less substrate to cause a cooperative change in shape. While an inhibitor, you now need an increase, right? As you can see here, an increase in the substrate for it to start changing shape to reach its Vmax. And as you can notice here, overall, the Vmax is increased here and decreased with an inhibitor. So far, so good, everyone?
Can you repeat this part, the graph?
Okay. Now, if you see how the allosteric activator and allosteric inhibitor, basically, this would help drive, an allosteric activator would drive the change in shape. Hence, you don't need the same amount, excuse me, hence you don't need the same amount of substrate, you need less for it to cause the cooperative shape change and then reach Vmax. If we look here, we said what? That only once substrate concentration reach a suitable amount will there be a change in shape that will drive a fast reaction, right? But if we look here, now there's an activator. So you need less substrate because there's something pushing it that is, because look, here, the only thing that will drive the change is the substrate. Here you have both a substrate concentration and an activator. And if you look here, you have an allosteric inhibitor. It is making it more difficult for the substrate to change the shape of the enzyme. So you would need more concentration to counter a higher concentration of the substrate to counteract the inhibitor. Hence why it is lower and it's shifted to the right. Tamam? So far so good?
Yeah, yes, thank you.
No problem. Now, obviously, allosteric enzyme should exist in two conformations. The T state has a low affinity. The R state, relaxed, has a high affinity for the substrate. In the absence of substrate, enzyme is in the T state. So, as you said, because the substrate at a certain concentration would change its shape, so it would be in the T. And once there's enough substrate, the enzyme will change, increasing the affinity, like we said, this will drive the change of reaction, right? Pretty straightforward, but remember what T state is, means what, and R state as well, because they can ask about it, and it's very straightforward concept. Now, regulation of allosteric regarding, again, what we discussed earlier regarding its activator inhibitor. We said they don't bind to the active site, right? But what happens is the inhibitor would keep it in the T state, making it harder and you need more substrate. While the activator would help change the active site, to become in the relaxed state, which is what the high affinity state. Straightforward. This is also now basically discussing another example of what do you call it? Active, sorry, what's it called? Allosteric activator or inhibitor. One is no modulator. This is the normal conditions, right? And two, it severely dropped. It kept the enzyme in a T state. So it made it very hard. It didn't even reach the Vmax yet, although the substrate concentration is significantly higher when others have reached Vmax. But if you look at 3, you gave an inhibitor and an activator. So although the activator wasn't able to completely neutralize the effect of the inhibitor, it was able to still improve the state of what can be seen at 2. Okay. And basically, it says here that the committed steps is what is occurred by allosteric enzymes. And this is also what feedback inhibition, which I've covered earlier, is once you reach enough product, you don't need more. So it inhibits it. This is called feedback inhibition. Same thing to ATP. Now, clinical insight. PRS is an allosteric enzyme in the purine nucleotide synthesis pathway. A mutation leading to the loss of regulatory control without an effect on catalytic activity leads to the overproduction of purine nucleotides. The overproduction results in the painful disease gout. Basically, gout is when there's basically gout is these crystals you'll find in the joints. But what they're trying to say is here, since now there is no negative feedback, so there's no way to control between the T and R states, what can happen is the enzyme would keep overproducing purine nucleotides, and the purine nucleotides would crystallize and form this thing that we see as gout. Now, let's do a little checkpoint real quick. Let's recap everything we've covered so far. So far, we've covered the concept of Km and Vmax. What is Km? Hello. Km is affinity, and the Vmax is basically the one substrate that's the highest concentration, its maximum activity. Okay? And Michaelis-Menten line-Weaver break graphs. We derived this graph from using the Michaelis-Menten equation that you can use. It becomes, this is a straight line. The key points, the key factors we understand of this graph is what do you call it? The y-intercept at 1 over Vmax, and the x-intercept is -1 km. We will cover this first. And then we also talked about allosterism, which is basically the change in shape driven by the binding of substrate, and there are factors such as activators or inhibitors that would affect the change in shape between the T and R states. And we also mentioned that the T state is the tense, otherwise low affinity, R is relaxed, high affinity, can bind, giving it what are the characteristic shape allosteric enzymes? Sigmoidal shape. Now, okay, here's a question for you, everyone. Km is the concentration at 1 over 4 Vmax. Is this true or false? Anyone? It is false because it is half Vmax, not 1 over 4 Vmax. And people feel more hungover due to what? Due to the low Km, so high affinity of the enzyme. As we said for the acetaldehyde dehydrogenase. And what is going on here? We said, obviously, this is a sigmoidal curve of the allosteric enzyme. You are given here an activator, and here's an inhibitor. And then lastly, allosteric enzymes are active in the R state. True or false? True. Obviously, not necessarily you can say active, but they have a high affinity in the R state. Okay, false and true, correct. Now here's the second part. What affects enzyme activity? We already covered in enzyme 1, the environmental conditions such as temperature and pH, and cofactors and coenzymes like NAD, FAD, etc. Now, enzyme inhibitors. This is basically what you'll see 90% of your questions from, everything regarding enzyme inhibitors. Inhibitors are chemicals that reduce the rate of enzymic reactions. They are usually specific and they work at low concentrations. They block the enzyme, but they do not usually destroy it. Many drugs and poisons are inhibitors of enzymes in the nervous system. Let's look at reverse. An enzyme inhibitor is a molecule that decreases the rate of an enzyme catalyzed reaction. Okay, straightforward. We already covered this idea several times. Now, reversible. It binds covalently. The difference here is between reversible and reversible is that in irreversible, it's covalent binding, while in reversible, it is weak interactions, so it can be removed. While here, irreversible, it binds covalently, and inhibition, it gets worse with time. So if you don't provide that necessary treatment as soon as possible, it will only get worse. And as I said, irreversible, it is by weak interactions, such as charge-to-charge, H bonds, or hydrophobic interactions. Now, we have 3 types: competitive, non-competitive, and uncompetitive, right? Now, before we cover these 3, let's look at an example of irreversible inhibition. As we said earlier, they inhibit tightly, often covalently to the enzyme, permanently inactivating it. Now, nerve gases and pesticides containing organophosphorus combine with serine residues in the enzyme acetylcholine esterase, thus blocking transmission at the neuromuscular junction. It is very important to know that nerve gases and pesticides, you'll see many questions, they won't tell you nerve gas or pesticide. They'll say a man was working in the farm using fertilizer, taking care of his farm, and then suddenly he came with symptoms of, for example, like problems at the neuromuscular junction. So there's flaccidity, etc. Breathing problems as well. And they wouldn't tell you directly it contains organophosphorus. You need to read the case to know that what was he exposed to, which is usually always pesticides. Now, in reversible inhibitors, the first one is competitive inhibitor. The inhibitor has close structural similarities, structure analog to the normal substrate, and therefore compete with the substrate for the active sites. Basically, if you look at here, here's the substrate and here's the inhibitor. And they both can fit like a key into the enzyme. Although at the other end, the other remaining structure of the inhibitor is not identical to the substrate, its shape is complementary to the enzyme for the active site, and that's all it needs to bind. Basically now, literally, the substrate and the inhibitor are literally competing. They are both fighting for the active site. So based on the concentration, it's what takes cover of that point, of the active site. And the only way we can remedy this is by giving more of the substrate, to push, basically, like to give a higher chance for the enzyme not to find the inhibitor, but to find the substrate in the given solution or in your body. If you're poisoned for something that works in a competitive inhibition manner, what you want to do is give now a positive substrate just to be sure, as you said, so the enzyme is more likely to find the substrate rather than just to find the inhibitor. Because what happens is once the inhibitor binds, the enzyme will no longer work. So the enzyme is no longer functioning. For example, there's no more ATP production. We don't want that. So we just give more natural substrate to drive the reaction. Now we look at the enzyme kinetics. In competitive inhibition, as I said, can be overcome by high S. The Vmax does not change, but Km increases. In other words, the Vmax, you notice here there is crossing, where at a given point, the different slopes between the enzyme activity in either, for example, in normal condition, and then when they say in the question they've given the toxin, you'll always notice that what's changing is occurring at the x-axis. The y-axis is unchanged, so it's giving you this cross effect. And a little way to remember, competitive shows crossing. Okay. And if you notice here, now we said that Km increases. What did we say what happens when Km increases? Its affinity decreases. And this does make sense. Why? We said that if the enzyme is not bound to the inhibitor, there's less enzyme, and now less enzyme available to react to the substrate. So there's now reduced capacity of the enzyme available in the solution or in the body. So if the Km increases, now look at how the formula is. It is usually, now we said it is 1 over Km, and this is a negative value. So let's assume we went from 1 over 2 to 1 over 4, right? This means the Km increased, right? In other words, its affinity decreased. But where will you notice the line on the graph? This is now -½ and -0.25, right? If you look at the line, what happens is, so let's assume this is the half, it will be shifted forward. It goes here. But yeah, exactly. But this is 1 over 2. Now, when you're given the inhibitor at high concentration, for example, in this example, the Km got shifted, it got higher. But since it's on the line, a higher Km, instead of going to the left, it will go further to the right. So it'll be here. As you can see, they give 4 units of the inhibitor here. And if you look at where there's no inhibitor, which is this one, this is the furthest to the left. But the more inhibitor you give, it will shift closer to the 0. Does that make sense?
Can you repeat this part?
Okay. The screen. razor. Now, let's look at the case where there is no inhibitor. Let's assume this is -1. Therefore, Km here is what? 1. Now we said what happens when we increase or when we give a high concentration an inhibitor, Km would what? Increase. It would go up. Therefore, the Km in this case is equal to 2, for example, for simple calculation, right? 2. And here at higher is now 4. We said earlier what the formula for, or on the graph, the y-axis represents half Vmax, sorry, not half, 1 over Vmax. And the x-axis represents -1 Km. Ignore the alpha, it's not necessary to worry about that. -1 Km. So when we're plotting the graph, right, we said that we have now here, so if we're plotting the graph, it would be -1 equal to 1. This would be -half. And this would be -1 over 4. In other words, -0.25, -0.5, and -1. And as you can see here, if you want to plot it, it goes from -1, this is what in normal. Then it goes to 2, so half, -half, so 0.5 over here. It got shifted to the right. So although we said Km increases, the number got smaller when we calculate it, right? When we put it on the plotting. And then we said here at the highest concentration of inhibitor, you now have -0.25. So it's the closest to 0. And a simple way to remember, the second you see, let me select all of this. Is okay, enough. The second you see all the lines converging on the y-axis, just know directly it's competitive inhibitor, because in the other two types of inhibition you will see, they will never cross each other. So C for crossing, competitive for crossing. Then C com equal cross, which as you can see here, they're all converging on each other. Tamam? Does this make sense? We'll cover the point again later, so inshallah by then. Now, an example of competitive inhibitor is HMG-CoA reductase, which is for cholesterol synthesis, the rate-limiting step, of course. And the HMG-CoA reductase, they're given the name statins, either atorvastatin or pravastatin. Always look for statin. It's, I think, almost always, it's anything related to cholesterol maintenance at your level. You need to know. Now, competitive inhibitors for HMG-CoA reductase. Yep. Now, regulation of enzyme activity inhibition by non-competitive inhibitors. They are inhibitors that bind to domain other than the active site, and they do not interfere with substrate binding, and they bind to either enzyme or enzyme substrate complex. Inhibition not reversed with active substrate from enzyme inhibitor plus substrate and EIS complex. Okay, in other words, not all of this. If we look here, they are now on the enzyme. It has multiple binding sites, such as the inhibitor. For the main site, of course, is the active site, where the substrate would typically bind. But if you give the inhibitor, it has its own site to bind to. So there is no competition between substrates. So giving extra substrate will do nothing, because the inhibitor on its own already has its own door to enter. So there's no issue joining or binding to the enzyme. And once the inhibitor binds, it will immediately, it will no longer let the enzyme do its job. Therefore, as you can see here in the enzyme substrate inhibitor complex, there is no product. Or even here, if the inhibitor reaches the substrate for the enzyme first, it would also cause no product. Because then the second this type of inhibitor binds, alas, the enzyme is now useless. Okay? And if we look at the kinetics, where is there crossing in the y-axis? No. So directly. But what will you see? You see converging in the x-axis here, basically. Basically, sorry, look at the y-axis. If there's no crossing, you can now cancel out this change in the enzyme activity is what? Competitive. It will be either now non-competitive or uncompetitive. And as you said here, that the Vmax will be affected because the inhibitor is now affecting the activity of the enzyme, not the binding to the enzyme. So since the binding to the enzyme is not changed, the Km would be relatively unchanged. It has no effect. And so usually, as you can see, this small change is very insignificant. But what happens is the main thing we need to look at is what the changes at the Vmax. Now it's now moving. And in this case, unlike the Km, if the Vmax decreases, the Vmax decreases. So let's assume we have here at normal conditions, assume the Vmax is 1. Vmax is 1. Okay, so now we have 1 over Vmax. If the thing goes up, so let's assume now we have Vmax got reduced 1 over 0.5. So that's now, so Vmax in the normal condition was 1, and now the Vmax in with this few inhibitor is 0.5, so that will give you 2. So it will be increased, it will go up on the y-axis. So it would also work oppositely. So although the Vmax would decrease, its position on the line would increase. And also same thing here. Let's assume here the Vmax became 0.1, 1. It's now 10, if my math is correct. So now the Vmax would even go further up on the y-axis. The one, it's also important to know the examples because they can tell you a child was exposed to lead paint. What is the inhibitor? What was the inhibitor he was exposed to? So على طول it is competitive, non-competitive, sorry, lead and heavy metal. Lead binds to the what? The substrate hydride side chain of cysteine of the ferrochelatase enzyme. You'll cover this later in the HLS block. But it's good to always note, be prepared for later on. Lastly, and what I used to think was the one that works the weirdest was the uncompetitive inhibitor. An uncompetitive inhibitor works similar to the way of the competitive, non-competitive, where it has its own site to bind to, all right, and it would directly bind to it. But what happens here is it would cause a change in both the Km and the Vmax. So what would you notice? You would notice that the lines are now always parallel. You always notice here there's always some kind of crossing due to the changes of any change in the Vmax, right? Either here or in the y-axis itself, right? But you'll notice that the lines will never cross, no matter where at any point in the line. There'll be no crossing. Why? Because that's when the Km and the Vmax decrease. So what happens is with every change, the line will go up and shift further to the right, further to the left. Yes. But why? No, because the way this inhibitor exactly works isn't explained in depth. But what happens is the change in the Km, it will increase its affinity. All right. Because the way this class of inhibitors work is it will make sure the enzyme will not let go of its substrate. And this in one way is, and when you calculate it, it is revealed that when the enzyme is not able to let go of the substrate, it shows a higher affinity. So the Km would decrease. Hence, as you can see here, the Km is now shifted further to the left with every increase. Because it looks like this one, where did it go? Looks like this case here, where the Km is the highest, or the highest. The affinity, the Km would be the lowest, where the affinity is highest. See how the way even I can get confused between the terms. So when we approach the questions, take everything one step at a time, and it will be very easy to deal with. But remember that what happens here what happens in uncompetitive, it will cause a decrease overall. Tamam? Now, summary. To summarize everything we've taken in this lecture so far, the Km and Vmax values and their graphs. What do you understand from the Km? It is the inverse of affinity. So if anything that has a higher affinity, it will have a lower Km value. And the Vmax is basically when there's maximum substrate binding and its maximum speed of producing it. And we discussed about allosterism, the T and R states. T is tense and R is relaxed. And this produces what? I
have a question, excuse me.
Yes, go ahead.
What is Vmax again? I didn't got it. So.
Okay, Vmax.
It is the substrate ولا ايه؟
you can use the amount of substrate used as a point of reference. You see, basically, if I give you a high amount of substrate, tamam, and you in a short amount, or not you, the enzyme in a short amount of time was able to use entirely all of that substrate, tamam. And what happens is, if you look at the graph here, we continuously would always now check where it goes, tamam. And basically, the Vmax is, if I give you the maximum amount of substrate, how much will you produce for me speed, tamam? And that means once the enzyme eventually reaches Vmax, no matter how much more substrate you give, the Vmax will not change, khalas, because the enzyme all the enzymes are now occupied and are producing the product. So no matter what substrate you give, it will not use it. It is the maximum ability or / activity of the enzyme. Tamam?
Okay, I got to thank you.
No problem. Now I believe. Okay, let's solve questions. But before we go ahead, category, we discussed also the categories of inhibitors, which are reversible and irreversible. We said that we have competitive, which would cause what? A change, a decrease in affinity. And then non-competitive, which would cause a change in the Vmax. And then uncompetitive, where, what do you call it? Would cause a decrease in the Km and the Vmax. So Km means it would increase its affinity, right? Higher affinity, because why? The way this inhibitor works is it will not let the enzyme let go of the substrate. So this means the affinity of the enzyme to bind to the substrate is higher. Tamam? And the Vmax would decrease. Tamam? Now let us discuss some questions. And as I said here, the trick to remember, if there is competitive on the y-axis, it is directly, if there is crossing of the lines on the y-axis, it is competitive. But if there is not, whether like the case here or here, it is now either non-competitive or uncompetitive. And how do you tell? Either by checking here, will there be crossing at any point before the y-axis, or are the lines running parallel? If the lines are running parallel and the changes occurring are like in parallel like this, it means it's uncompetitive. But if there's no crossing on the y-axis, but at any point before, it means there's slight changes in the Km, or not, sorry, as the Vmax, it is going to be non-competitive. And let's now apply what we learned onto questions. This one was from a previous batch question. Tamam. 5 times 10 to the power 6 is the Km. Negative 6 is the Km. In other words, the inverse of affinity. And the Vmax of 20. What will be the rate when substrate levels are 5 times 10 to the power negative 6? I will not answer. I want someone to volunteer. Anyone? Okay. Now before we approach this question, let's see what do they want. They want the Vmax. They give us the Vmax and the Km. What can we combine with this information? We know that Km is equal to half V max. Now, with this formula, what would be the answer? I can't open chat. Okay. So there, guys, there's no wrong answer because we can always learn. فعادي. $10. Exactly. Why? Thank you. 221684. Where is the pen? 10. Exactly, it's 10 because what? We already خلاص. We know the Km is this. And they tell you that at the substrate level, it is the same. So 5 times 10 to the power -6. معلش على handwriting is equal to the half of 20. So على طول is equal to what? 10. طبعا. See, this is very simple. If you remember the formula, you would directly know how to answer this. تمام? Now, to the next question. Let's look. A 40-year-old tobacco farmer is seen in the ER with bradycardia, profuse sweating, vomiting, increased salivation, and blurred vision. He was spraying his fields with malathion when the hose ruptured and he was covered with malathion. Which of the following types of inhibition of enzymes does this poisoning represent? That A, competitive, B, non, C, irreversible, D, irreversible, E, the drug does not work by inhibiting enzyme activity.
C.
Why C?
عشان irreversible precise على farmer spray
بالضبط. Thank you. Exactly. خلاص. They told you in the case, even if you don't, let's assume you didn't know what malathion is, but they told you spraying his fields. But obviously he's a farmer, and these are what are at risk to what? Irreversible enzymes and reversible inhibitors. And sometimes they could contain what? Organophosphorus. تمام؟ organophos. إلخ مش automated. تمام؟ يلا, the next one. 23. 28-year-old female presents with fluctuating fatigue, drooping of her eyelids, difficulty swallowing, and slurred speech. The patient is given a drug that affects an enzyme's activity, and kinetic analysis of the enzyme catalyzed reaction. In the presence and absence of the drug is shown below. The effect of this medication can be described by which of the terms below? Quickly, before, what do you see here?
intersection في y axis.
Exactly. So therefore, it is
competitive.
Exactly. So خلاص على طول, now we ignore all of this. All of this is useless to us. Either A or B. Now.
A. Vmax unchanged will increase.
Exactly. Did everyone else understand? No. Okay. I'll explain again. Please explain. No problem. Eraser. Where is it? أولاً, let us review what are the types of enzyme inhibitors, right? Okay, so we have uncompetitive, non-competitive, and where is it? Competitive. Different enzymes work, different inhibitors has different effect on the enzymes. A competitive inhibitor, basically both the substrate and the inhibitor are both fighting for the same active site. They both want to bind. Tamam? So when you have two people fighting for the same place, the enzyme will be confused on which one to take. So its affinity or its ability to grab a certain item, either the substrate or the inhibitor, is reduced. And therefore, its Km would be increased. A change in Km, we said Km is inverse to the, changing Km is inverse to the affinity. So if the enzyme's affinity is reduced, its Km would increase. And therefore, with an increase in Km, you will notice the line will shift to the right. But an easy way, if you just forget all of these rules, to identify directly if it is either either competitive or uncompetitive or not competitive, is what to observe. Is there crossing on the y-axis? Because competitive is the only thing that will not affect the Vmax. So the Vmax, they will all converge, doing what? Crossing. So remember, it's competitive for crossing. Why? Because the Vmax is unchanged while the Km is changing. Hence, changing the x-axis, but not on the y. Does that make sense? So now if we look here at A, the competitive, so directly we saw there's crossing on the y. Khalas. Ignore all of this, we don't need this anymore. Now let's look. Effect on Km. Tamam. Increased or no? One, it is we said that the Km is increased because its affinity is what? Decreased. Okay, yes, great. يلا اللي بعده. Can you answer this one? What is the mechanism shown of the medication? طبعا, let's tell me what's the first thing that is wrong. Who wants to answer? B. Non-competitive. Okay, I will show you why it is B. Let's go them down one by one. Is it C? لا.
لا reverse.
It is reversible. Straight line. Michaelis-Menten, so it's reversible. تمام? Now, is it allosteric? Do you see a sigmoid shape? لا.
No.
Not allosteric. The drug is not an inhibitor, rather it is an activator. Maybe, maybe it could be. Now, competitive or non-competitive? Is there crossing? لا.
No.
No, not competitive. So now, it's either B or E. Now, we said what happens in non-competitive? The Vmax changes and Km will stay unchanged. So if Km خلاص, because you're not affecting the affinity to the substrate. You're affecting the activity of the enzyme itself. So على طول مظبوط. It is B because the Vmax is what changes. In the presence, it is B. Correct. Why is it not an activator? Because we said what? In the presence of the drug, the Vmax is on the table, went up. And we said that earlier, 1 over Vmax, and we showed the example, where is a table. The lower the number of the Vmax, the higher it would be on the graph. So let's assume the Vmax got reduced by half, it will go up on the graph double. So you're correct, it is B. Last question. Then we can take a break, pray, and continue the next lecture. What's the answer for this one? You want to measure the total amount of enzyme in a specimen. Which value of substrate should you use? A. Is it A? No, it's not A. What is it? Try again. Not A. طيب. بما إنه we are looking at this, the initial velocity. Let's go back. Where is it? Initial. Let's look here. Do you notice how that the initial velocity is just at when it reaches its peak in a short amount of time? Once you've given the product concentration. So once you've given the substrate, within a short period of time, the highest amount of product is produced. So if we go to the question, we go to the question, we want to see what do we do to see the speed? We give you as much substrate as you can and see how far it goes. So obviously at 0.5, it produced 10. Could it be the initial velocity? Maybe. How do we know? When we gave more substrate, did the speed increase? Yes. Therefore, it can still have more. So when we gave 1.5, is it still increasing? Yes. Up 2, yes. Now, let's look at 2.5 and 3. Here, as you go here, you notice the difference in the increase. First, it was 50. Then it was 40. Then it was 20. Here, from 120 to 129, the increase is only by 9. And then now we're plateauing at 130. Difference of only 1. So if you look at the graph where the substrate is basically almost approaching the peak activity of the enzyme, that's going to be your answer for what would give you something you should use to help calculate the total amount of enzyme in a specific. It's D. Tamam. So basically, just look at where does the enzyme start plateauing in activity. Tamam. Does that make sense? Okay. Now we will take a short break to pray and continue soon.